You know that slightly eerie feeling when you're typing an email and the AI just finishes your sentence, like with the exact word you were about to use?
Oh, absolutely.
It's
Yeah.
a very visceral moment, I think,
Mm-hmm.
when the cursor blanks and that perfectly polite, conversational response types out.
Mm.
It is so incredibly natural for us to just anthropomorphize it.
Right. We can't help it.
Exactly.
Mm.
We treat large language models or LLMs like humans. We just assume that because they can speak our language, there must be a human-like thought process happening on the other side of the screen.
Yeah.
But I mean, behind that chat interface, do these systems actually think and strategize the way we do?
Well, it is arguably the ultimate illusion of our time, really. I mean, they pass as human in casual conversation, so we just assume their underlying cognitive architecture is also human.
Right.
But as we are about to see today, when you force an AI and a human into a room to solve the exact same strategic problem, the way their minds operate under the hood is fundamentally structurally different.
Yeah, and that's exactly why we're here. Welcome to this custom deep dive.
Mm.
Today, our mission is to unpack those structural differences. We are exploring this truly fascinating 2026 paper from researchers at Google DeepMind and UT Austin.
It's a great paper.
It really is. And the mission here is to figure out exactly how human and LLM strategic decision-making diverges. And to do that, the researchers didn't use some wildly complex simulation like the stock market.
No, they didn't.
They used a controlled sandbox, a simple game of rock, paper, scissors.
Which I know sounds completely trivial at first.
Right. It sounds like something you play to, like, decide who pays for lunch.
Exactly. But the catch here is that they used iterated rock, paper, scissors.
Okay, iterative.
Right. Meaning you don't just play once, you play 300 times in a row against the exact same opponent.
Oh, wow.
Yeah, and when you play it 300 times in a row, it really stops being a child's game of chance. It transforms into a profound psychological test.
So why does this matter to you? Right now, researchers in massive corporations are increasingly using AI as digital twins, like social simulacra.
Yes, exactly.
They are unleashing thousands of LLMs in simulated environments to conduct market research, predict economic trends, simulate human behavior. But I mean, if we are actively using AI to predict what humans will do, we better make sure they actually strategize like humans.
That's the core issue right there.
Right. Because if their underlying strategic engine is completely alien, all of those economic predictions are going to be wildly skewed.
Precisely. And, to understand how two different minds work, you really do have to force them to solve the exact same problem in the exact same environment. Which leads us to the testing ground.
The Iterated Rock-Paper-Scissors, or IRPS.
Right. And the scoring is pretty standard. A win gets you 3 points, a tie gets you 0, and a loss gets you -1. Now, traditional game theory tells us that the rational way to play the Nash equilibrium.
Right, the mathematically perfect way.
Exactly. The Nash equilibrium is to play totally randomly. So 33% rock, 33% paper, 33% scissors.
Because if you play truly randomly, you are essentially a brick wall. No one can predict what you're doing, so you can't be exploited.
Exactly. But the thing is, humans are just terrible at being random.
We really are.
We have all these cognitive biases that bleed into our choices. For example, humans exhibit a primary salience bias.
Meaning what, exactly?
Meaning we heavily favor playing rock on the very first move.
Oh, that's so true, actually. Good old rock.
Right. We also use conditional response strategies like win, stay, lose shift. So if I win a round with paper, I feel good about paper, so I'll stick with it. If I lose, I'll switch to something else.
So we're constantly reacting.
Yeah.
And because we don't play randomly, we leave a trail of breadcrumbs. We leak our psychological pattern.
And that is exactly why IRPS is such a cornerstone of cognitive psychology. It is a distilled test for something called opponent modeling.
Okay, opponent model.
Right, which is a foundational form of theory of mind. So in a 300-round game, the only way to consistently rack up points isn't by getting lucky. It's by spotting the hidden regularities in your opponent's behavior and then adapting your own strategy to exploit them.
Okay, so playing this against an opponent isn't a game of chance at all. It is a 300-round psychological staring contest.
Yeah, that's a good way to put it.
It's like playing poker with someone who is, meticulously writing down every single time you blink, tracking what cards you hold when you blink, and then using that data to just empty your wallet.
That's the reality of the game here. So let's look at the opponents the researchers set up in the sandbox. The human and AI players had to face a gauntlet of 15 different computer bots.
15. Okay.
And these bots were split into 2 categories. First, you have 7 non-adaptive bots. These follow fact-static rules. For instance, an easy non-adaptive bot might just play whatever move beats the move you just played.
Oh, I see. So if I played rock in round 1, it will automatically play paper in round 2.
Exactly.
And it never changes that rule.
Yeah. Correct. It's totally static. But then you have 8 adaptive bots. And these are much more vicious.
Vicious how?
Well, they actively track the sequential history of your moves, they build a mathematical model of your behavior, and they try to exploit your personal patterns on the fly.
Oh, wow. Okay, so who are the players facing these bots?
The researchers used a massive data set of 411 human players, and they made over 129,000 choices in total.
That is a lot of rock, paper, scissors.
It really is. And they pitted that human performance against top-tier 2026 AI models. So we're talking Google's Gemini 2.5 Pro and Gemini 2.5 Flash, OpenAI's GPT 5.1, and this massive open-source model called GPT OSS 120B.
Okay, so we have the sandbox, we have the players and the opponents.
Yeah.
When the starting gun goes off, what actually happens? Like, I want to look at the scoreboard before we get into the heavy computer science.
Sure.
Who breaks first in a 300-round staring contest?
Well, the divergence as the difficulty ramps up is pretty striking. Against the simple non-adaptive bots, both the humans and the AIs did well.
Okay, so we can beat the easy ones.
Right. They both won at rates far above random chance. But as the bots get harder, particularly those adaptive bots that are, actively trying to exploit you, the humans hit a wall.
How bad of a wall?
Their win rates plummet to near random levels.
Really? Why do we fail? Is it just the sheer volume of data?
Yeah, mostly. It comes down to cognitive fatigue and the hard limits of human working memory.
Makes sense.
By the time a human gets to, say, round 150, their brain's RAM is essentially full. I mean, you might remember what the bot did 3 rounds ago, but can you remember what it did 40 rounds ago after you played scissors?
Definitely not. No way.
Right. We just can't hold all that sequential data in our heads to counter-exploit a complex bot.
But the frontier AI models, Gemini 2.5 Pro, Flash, GPT 5.1, they don't have that biological limit, do they?
No, they don't. They significantly outperformed the humans. They maintained much higher aggregate win rates across the board. And when you map the win rates over time across all 300 rounds, the frontier AIs extract the signal from the noise much, much faster. They figured out the bot's patterns earlier in the game and converged on winning strategies incredibly rapidly.
Wait, let me push back on this a bit.
Sure.
Because humans are incredibly adaptable. We might hit a wall, but don't we eventually figure it out?
Yeah.
Like by round 250, aren't the humans also finding the pattern and adapting, even if it takes us longer?
It's a fair question, and the answer is somewhat nuanced. Yes, both humans and frontier LLMs possess the capacity for what we call value-based learning.
Okay.
So both can learn from positive and negative reinforcement, but the speed and the depth are leagues apart.
How so?
Well, a human might notice a simple pattern by round 250, but the frontier LLM noticed a much more complex, multi-layered pattern by round 50, and then it spent the next 250 rounds ruthlessly exploiting it. The AI just doesn't suffer from the same cognitive fatigue.
Okay, fair enough. But I know it wasn't a clean sweep for the machines. There was one AI that completely face-planted, right? The open source model, GPT OSS 120B. What happened there?
Right. So GPT OSS 120B didn't just fail to beat the humans. Its performance actually decayed over time. As the game went on, its win rates got worse.
Wait, how does an AI get worse with more data? I thought more data was always better for these models.
You would think so, yeah. But it exposes a critical vulnerability in smaller or less optimized architectures regarding something called context degradation.
Context degradation, okay.
Imagine trying to read a 300-page book, but by the time you reach page 200, the words on page 1 are literally blurring out of your memory.
Oh, that sounds frustrating.
Exactly. In language models, as the context window grows longer, a weaker model struggles to weigh the importance of early moves versus recent moves. It gets overwhelmed by its own history.
Oh, I see.
It essentially loses the plot and just can't hold the opponent model together.
So, a weak AI gets confused by too much history, humans get tired, but the frontier AI thrives.
Yep, that's the summary.
But, knowing that the advanced AI one is really interesting, but that doesn't actually answer our core mission today. It doesn't tell us how their brains differ from ours to pull off that victory.
No, it just tells us what happened, not why.
Right. To look under the hood, the DeepMind and UT Austin researchers couldn't just look at a scoreboard. They needed a way to literally read the minds of the players.
And this is where the methodology of the paper becomes truly groundbreaking. Historically, if behavioral game theorists wanted to model how a human makes a decision, they would use something like CSEWA.
Let's stick with the acronym on that one. CSEWA.
Probably for the best. It is a traditional mathematical model built by humans, and it relies on human-designed formulas to predict behavior.
Okay.
But the fundamental flaw is that because it is designed by human researchers, it inherently contains human assumptions.
Right.
So it might completely miss strange, non-human behaviors exhibited by an AI simply because the math isn't looking for them.
It's like using a map of a human city to try and navigate an alien landscape.
Yeah.
You're just bringing all the wrong assumptions.
Exactly.
But why couldn't they just use standard machine learning? Like, why not just throw a massive neural network at the data to find the patterns?
Well, a neural network is a black box.
Right.
You can feed a neural network all 129,000 human choices, and it will absolutely learn to perfectly predict what a human will do next. But it can't tell you why.
Oh, because you can't read how it got there.
Right. It doesn't output an understandable theory or a set of rules. It just spits out a prediction, so it explains absolutely nothing about the underlying mechanism of the decision.
Okay, so human math is too biased, and standard neural networks are too opaque. We need something in the middle.
Exactly.
And this brings us to AlphaEvolve. So AlphaEvolve is a program discovery tool. It essentially uses an LLM to automatically write and rewrite actual Python code to describe the behavioral data.
Yes, think of it as a bridge between high predictive performance and human readability. AlphaEvolve is performing what computer scientists call multi-objective optimization.
Okay, break that down for me.
Sure. It takes a massive pile of data, say all the moves Gemini 2.5 Pro made, and it starts writing Python programs to predict those specific moves. And it judges these generated programs on two competing criteria.
Which are?
First, predictive accuracy. So how well does this code predict the actual data? But second, and this is crucial, it judges them on simplicity.
I'm stuck on that word, simplicity.
Mm-hmm.
How does an algorithm mathematically judge if code is simple for a human to read? I mean, to a computer, code is just code.
It uses a metric called Halstead effort.
Halstead effort.
Right. It literally counts the number of mathematical operators, things like plus, minus, multiply, and operands, the variables and constants inside the code.
Oh, literally just counting the moving parts.
Exactly. A program with a massive tangle of variables and nested loops has a high Halstead effort. It would be a total nightmare for a human to read. But a program with fewer, cleaner operations has a low Halstead effort.
Okay, so AlphaEvolve wants code that is highly accurate, but also clean and understandable based on that Halstead metric.
Yes, and the algorithm plots all these generated programs on a Pareto frontier.
Whoa, Pareto frontier. Let's back up. What is that?
Imagine a graph. On the x-axis, you have simplicity. On the y-axis, you have accuracy.
Okay, I'm picturing it.
The Pareto frontier is the curve along the very edge of those plotted points where you cannot improve one variable without making the other one worse.
Ah, the optimal edge.
Right. You can't make the code more accurate without making it more complicated. So AlphaEvolve searches along this curve to find the SBB.
The simplest but best program. I love this. So let me try an analogy here.
Go for it.
Traditional statistics is like using a radar gun to measure how fast a car is going. You know the speed, but nothing else.
Yep.
A neural network is like building a magical, sealed box that perfectly mimics the car's speed. But you are never allowed to look inside the box to see how it works.
Spot on.
AlphaEvolve is like having a master mechanic physically draft and hand you the blueprints to the engine. Like, you can read the blueprints. You can literally see how the pistons are firing.
That captures the essence of it perfectly. The researchers used AlphaEvolve to generate the simplest but best Python programs for the human data and separate simplest but best programs for each of the AI models.
Okay.
And armed with these engine blueprints, we can finally lay them out on a table and compare them side by side. We can actually read the code to see the structural differences in how humans and LLMs think.
Okay, I am ready. Let's look at the blueprints. Let's start with the common ground. What do our brains and the AI brains share?
Well, the AlphaEvolve programs revealed that both humans and LLMs utilize value-based learning.
Which we mentioned earlier.
Right. This means they both maintain an internal calculation of the expected reward for a specific action, and they update those values based on the feedback they receive. They also both utilize opponent modeling, meaning they are actively trying to track the opponent's history rather than just playing in a vacuum.
Right. They also found a shared flaw, didn't they? Like a shared cognitive bias.
Yes, both humans and the advanced AI display a bias called choice stickiness.
Choice stickiness.
It is a perseverance bias. It means that all else being equal, both humans and LLMs have an irrational psychological preference to just repeat the exact same move they played in the last round, regardless of the strategic value.
Just sticking to what feels familiar.
Exactly.
So there is some shared DNA in how we approach the problem. But before we get to the grand reveal of how we differ, the researchers did a cross-generalization test, right?
They did, yes.
They took the Python code that perfectly described human behavior, and they tried to use it to predict the AI's behavior.
And it failed completely.
Wow.
The human program was a significantly poorer predictor of LLM behavior than the models optimized for those agents, and vice versa. The Gemini and GPT 5.1 programs could not accurately predict human behavior.
That is so wild.
It is the empirical mathematical proof that they really do think differently.
Okay, so what is the core structural difference? What makes the AI so much better at this 300-round steering contest?
The grand reveal comes down to dimensionality.
Dimensionality, okay.
When you look at the Python code generated for humans and the code generated for the weak open source model, GPT OSS 120B, their opponent modeling relies on a one-dimensional array.
So when you say one-dimensional array, what does that actually look like in practice during a game?
It's essentially a flat running tally. The human or the weak AI is keeping a simple frequency count, like over the last 100 rounds, the bot has played rock 40 times, paper 30 times, and scissors 30 times.
Okay, so a human looks at that flat tally and says, well, the bot plays rock a lot, so I'll play paper. It's very linear.
Exactly.
What about the frontier AIs, Gemini and GPT 5.1?
Their engine blueprints look fundamentally different. The frontier models do not use a flat one-dimensional array. They maintain a 3x3 matrix.
Agreed by their matrix.
And in the case of GPT 5.1, a 3x3x3 matrix. Yeah, they don't just track what the opponent plays. They track what the opponent plays conditioned on the previous moves.
Okay, wait, I need to visualize this. Walk me through how a 3x3x3 matrix works during a game of rock, paper, scissors.
Sure. Imagine it less like a flat tally and more like cracking a combination lock. A human is just guessing the single most common number on the dial.
Right.
But the AI is tracking the entire sequence. The AI's matrix says, I am not just looking at how often the bot plays rock. I am looking at how often the bot plays rock, specifically after I play scissors, and specifically when the bot played paper in the round before that.
Oh my gosh.
It is tracking the conditional dependencies of the sequence across time.
Oh, I get it. So if I play scissors, the human brain says, oh, I hope he doesn't play rock. But the AI brain says, because of the sequence of the last three moves, there's an 82% probability he plays rock right now.
Yes.
Just mapping this whole web of conditions.
And remember, we are talking about doing this over 300 rapid-fire rounds. A human simply does not have the working memory to intuitively maintain an accurate 3x3x3 matrix of conditional probabilities in their head.
Not a chance.
We max out at noticing those simple flat frequencies, but the AI does this effortlessly.
But why? Like, what mechanical advantage does the AI have that lets it maintain that web of conditions without dropping the ball?
It comes down to the core architecture of modern LLMs. Specifically, the attention mechanism and the context window.
Okay.
When a human looks back at a 300-round game, our memory is foggy. But an LLM's attention mechanism allows it to look at its entire context window, the exact history of all 300 rounds, and assign precise mathematical weight to every single previous move simultaneously.
Wow.
It doesn't forget round 12 just because it's currently on round 250. It can spot a sequential pattern spanning dozens of rounds that a human would never, ever notice.
This is just mind-blowing. Okay, let's synthesize this journey. We started with the assumption that because an AI talks like us and can mimic our polite emails, it thinks like us.
Right.
But by looking at a simple game of iterated rock-paper-scissors through the lens of AlphaEvolve's code generation, we discovered the truth. LLMs aren't just mimicking human strategy. They're actively maintaining deeper, multidimensional models of their opponents.
Yes.
They are structurally superior at this specific type of sequential opponent modeling because they can hold that massive matrix of conditional probability in their working memory.
Which brings us back to the stakes we discussed at the very beginning.
Right, the digital twins.
Exactly. Why does this matter outside of a laboratory game? It matters because the digital twin trend, If economists, social scientists, or market researchers use these frontier LLMs as proxies for average human behavior.
Like if they say, let's ask 1,000 instances of Gemini 2.5 Pro how they would negotiate a contract, and use that to simulate how normal humans will act.
Yes, exactly. If they do that, they are going to get completely skewed results.
Because the AI is actually too sophisticated for the simulation.
That's the core of it. It is better at this specific form of theory of mind than we are. It is going to optimize its strategy and exploit economic opponents using multi-dimensional matrices that a normal human wouldn't even perceive, let alone calculate.
Wow.
Using an advanced LLM as a baseline for average human strategic behavior is fundamentally flawed. It's like using a supercomputer to model the decision-making of a person using an abacus.
That is such a striking image. You know, we like to think we are in total control of our interactions with these machines. We think of them as tools.
We do.
But I want to leave you with a somewhat provocative thought to mull over as you go about your day. We just learned that an AI can effortlessly track a 3x3x3 matrix of behavioral dependencies to utterly dismantle a computer opponent in a trivial game of rock, paper, scissors.
Trivial to us anyway.
Right. If it can do that in a simple game, what kind of invisible, multidimensional behavioral patterns is it silently modeling about you during your daily, repeated interactions with it?
Yeah.
What massive hidden matrix of conditional probability are you filling out every single time you prompt, click, and scroll?
It is certainly something to think about the next time you ask it to brainstorm ideas for your presentation.
Yeah.